Okay, so today's lesson is on alkenes and alkynes. Alkenes have at least one carbon-carbon double bond, where alkynes have at least one carbon-carbon triple bonds. Both alkenes and alkynes can occur in cyclic structures. The general formula for each of these is given here. And again, the general formula is very helpful when it comes to identifying an alkene or an alkyne just from the chemical formula. Scientists use the term aliphatic hydrocarbon to describe any straight chain branch cyclic hydrocarbon. So that includes alkanes, alkenes, and alkynes. It's not used very often, but I wanted to include it. I also want to spend a little bit of time talking about the term functional group. A functional group is a group of atoms within a molecule that determines the properties of a chemical. So it generally is the place where reactions occur. And a carbon-carbon double bond, triple bond, a carbon double bond to oxygen, OH, are just some examples of functional groups, and we will see more as the unit continues. And we classify compounds according to their functional group because it really speaks to the functionality of the molecule. When it comes to naming alkenes and alkanes, spend a few minutes and take a look at the naming rules here. Essentially, the double bond or the triple bond becomes the entire focus of the molecule. And so when we are now looking for the longest continuous chain that contains the double or triple bond, the numbering of the longest continuous chain is based on the positioning of the double or triple bond. We want the lowest possible numbering on the double or triple bond. So what we'll do here is we'll go through some of the naming based on those rules. Again, please make sure you've referred to the rules so you understand the basis of what I'm doing. Okay, so here we're going to take a look at the longest continuous chain. Now you can actually see that it's straight across here. It wouldn't matter if you actually started here and did an L shape because this carbon is a point of symmetry no matter if you do the L shape or you do straight across. On the second carbon, the second carbon from this side, there is a CH3 group. Now number this, we're going to number from this side here because we want the lowest possible numbering on the double bond. The substituents are important, but the double bond takes priority over the substituents. So we're going to number from this side. So we'll have a double bond on 1 and a methyl on 3. So this particular molecule will be 3-methyl but 1-ene. Now, it's not always necessary to include the 1. It's not wrong to include the 1. You must include the positioning of the double bond numerically, and we embed it. This is the most modern way of naming. However, if there is no number indicated, it's assumed to be on 1. In this molecule, the longest continuous chain is the ring. Now, when we go to number this, again, we want to make sure that we're focused in on putting the lowest possible numbering on the double bond. Now, you can play around with this for a while, but what you'll find if you're getting the lowest possible numbering, the double bond, the numbering must pass through the double bond, and it must be the lowest possible case. So here, this carbon would be 1, that would be 2, then the substituent would be 3. If we numbered it the other way, the substituent would have a much higher number. So we do want to sort of consider this in the argument, but remember, the deciding factor is the positioning of the double bond. So take a second here and see if you can name this, and then check in with me in a moment or so. So hopefully this is what you saw, what you named it. Notice the cyclo is important because it indicates that the longest chain is actually a ring. It's a 6-membered chain, 6-membered ring, so that's the hex. The position of the double bond is on 1. That implies that the next carbon 2 is also part of the double bond. And based on that numbering, the methyl is on 3. Excellent. Let's take a look at this case over here. And the ending here is going to be different because this is an alkyne. So it will have the corresponding value. Let's take a moment and find the longest continuous chain that contains the triple bond in this case. I think what you're going to see is that this carbon here is a point of symmetry, so it doesn't matter if you go straight across or down. The longest continuous chain, let's just make it easy on ourselves, is straight across. Now, when it comes to numbering, we want to number from this side. And the reason is that the triple bond shows up on 3, and that's the priority. Here, it would show up on 4 if we came at it from the right side. Don't be too concerned about the substituent here. The substituents are important. If the triple bond showed up smack dab in the middle and it wouldn't matter which side you numbered it from, then the next point of discussion becomes the positioning of the substituent. But in this case, it's clearly that we want to number from this side. So take a moment, name it, and then check in with me. So hopefully this is the same name that you got when you worked through this. Again, hept 3-ine, it's a 7-membered ring. On the 3rd carbon, between the 3rd and the 4th carbon, is the triple bond, and the ending and YNE indicates that. On the 5th carbon, we have an ethyl group. So in these next 2 compounds, we want to spend a bit of time discussing what happens when we have more than one double bond or more than one triple bond. There are cases where you have a mix of double and triple bonds, but we won't be exploring those cases in grade 12 chemistry. So let's take a look here. When you take a look at this molecule, let's first count the total number of carbons. 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be an oct. There are 3 double bonds, and so we will use the -ine ending because it's an alkene, and we're going to embed the prefix tri because there are 3 double bonds. So when we construct this name, what you'll see is that we have the oct indicating the longest continuous chain. We have the positioning of the double bonds, and we're going to, what you'll see is it won't matter if you number them from the left side or the right side, because this molecule is perfectly symmetrical. The double bonds will start on 2, 4, and 6. Notice also you must embed the tri here in order to indicate that there are 3 double bonds. So that's really important to know. Now that being said, see if you can name this one based on what you saw here. So here is the way we name this compound. So it's very similar to the previous compound, except we're dealing with triple bonds. Again, you'll notice that the tri has been embedded to imply that there are 3 triple bonds. The YNE ending tells us that we're dealing with triple bonds. And of course, we have the locators 2, 4, and 6. I realize that it's a bit strange to have an I right next to a Y, but we sort of suspend the general rules of spelling when it comes to chemistry. Next, I'd like to look at these 2 compounds. Now, you'll notice that the way we have laid out these compounds here with the double bond is quite different than, say, the previous case up here. In the previous case, the one at the top of the page where the cursor is, you'll see that we've sort of used a condensed formula, and there's really no indication of how things are arranged around that double bond. If you get something like this, where the double bond is splayed out and it's very clear how the substituents are, or how the main chain is sort of conformed around that double bond, there is a special way that we have to look at these. So first of all, let's just try and name them as they are without any more information. So if you go to name these compounds with just the information we have so far, what you would find is that we would name them in an identical way. And yet, these compounds are different from one another. These, again, are a form of isomerism. So the thing about these is you need a different way of indicating them from one another. And the way that we actually do this is we draw a line through the double bond in a central kind of way through the axis of the double bond, like this, right across here. And if the longest continuous chain stays on the same side, like this, or if it goes across the double bond, we have two different ways of indicating that. Across the double bond, sort of on a diagonal, the prefix we use for that is trans. And if you think about transatlantic or translocation, it means across. And so in this case, the double bond, the bond axis moves across the longest continuous chain. It moves across the axis through the bond angle of the double bond. If it stays on the same side, like this, then what we understand it to be is we call it cis. So the indicator cis tells us that the longest continuous chain stays on the same side as the axis drawn through the double bond, where trans goes across, the longest continuous chain goes across the bond angle, across the double bond. So here is some details about cis-trans isomers. The other way that they're discussed, they're called geometric isomers. So you'll notice that when we put this into ball and stick model, there's some serious differences in the way these look. It's really good at showing the conformation. So notice that they're all sort of on the same side of the axis that would be drawn straight across. So if I draw sort of the axis straight across here, or if I draw the axis straight across here, it's really well displayed with this particular type of modeling. So again, there's the cis and trans identifier explained here. Now, I always get the question, Miss, when is it that I'm going to need to include cis or trans? Well, if you have a condensed structure like this, and focus in on the double bond here, where there's no way of knowing if it's cis or trans, don't worry about including it. However, if all of the groups are very clearly displayed in this way, so you've got the double bond and everything is sort of splayed out, in these cases, this is where we want to include cis or trans. Now moving on to reactions of alkenes and alkynes. This reaction we studied already in the formation of alkenes, and it's an elimination reaction with an alkyl halide. So you'll see this from the alkyl halide section. Again, you'll notice here that there's a Br. The Br group leaves, and on either side, a double bond potentially could be formed, and water is formed also. And I think we went through this, how this actually happens. So there's a whole bunch of electrons here, high electron density. These electrons pull off this particular hydrogen. And if you think about HOH plus a hydrogen, that's how water's formed. These electrons migrate down and help to form the double bond. And these electrons here are forced onto the bromine, and this forms the bromine ion. So that's how that reaction occurs in terms of a reaction mechanism. You're required to know that reaction. Now, addition reactions are just that, literally adding. This is similar to synthesis from grade 11 and grade 10, except addition usually means over a double bond or over a particular functional group. So again, I want to point out the similarities and differences here. If you start off with a double bond and you react it in the presence of hydrogen, these two blue hydrogens add right over the double bond. And they technically add cis, they add on the same side. If, however, you start with a triple bond and you're going to add hydrogen, notice you're going to need an additional number of hydrogens here. So here you only needed 2 total, here you're going to need 4. And in order to react a triple bond, you're also going to need to add catalyst and heat. You are required to know these reaction conditions. And again, you can go all the way to propane. So notice you can start with 2 different reactants here and end up with the same product. But how that happens, the number of hydrogens and the conditions are different. This last example is important to know. Notice that there are 2 double bonds. You need a total of 4 hydrogens here, but the conditions are the same as the top case, meaning that there's no triple bond. In this case, it's 2 double bonds at room temperature conditions and 4 hydrogens that will produce this. So these are really important to know the differences between them. Next, we'll move on to halogenation. This is also an addition reaction. So again, it adds right over the double bond. In the previous case, when we looked at adding a halide to an alkane, it reacts by substitution. Something comes in and something goes out. Similar to a single displacement, right? Here, this is addition. So you actually add 2 halogens over the double bond. If you start with a triple bond, the first thing that happens is you form a double bond. And again, notice that it forms in the cis conformation. It adds over the same side of the double bond. And that can continue to form a alkyl halide that actually has 4 halogens attached to them. Now in this case, we're now looking at hydration, and this is an important difference. In the 2 cases we looked at before, what was adding over the double bond was symmetric. So notice like HH or BR. And so in those cases, there's only one possible product. Things get more interesting when you have something adding over the double bond that's asymmetric. So if you notice here, we're adding water, and I've rewrote water instead of H2O as HOH. Notice the colors here, so it's easier to follow. There is a very interesting set of conditions when the double bond is placed in the molecule asymmetrically. So this molecule is going to have a double bond on the first carbon in. It's not symmetrically placed. So if I drew a line here of symmetry, what's on the left side and what's on the right side would be different. So the double bond is placed asymmetrically. Here, water is also asymmetric. So this is one possible product, but not the only one. I'm going to draw for you the other one. See if you can predict it. Okay, so let's consider that the OH could actually add opposite. You could have the OH on the first carbon and the hydrogen on the second. So these are 2 separate potential products. And this is what happens under these very specified conditions. You have a asymmetric placement of a double bond, and the reactant that's adding over the double bond also is asymmetric. If you have these conditions, both points of asymmetry, you will have 2 potential products. So this hydration example is just one. Now, it's important to know that they're not formed equally. And we're going to talk about that, how we predict who's the major and who's the minor product. So let's have a look at hydrohalogenation. Hydro meaning hydrogen, halogen meaning a halide. So here, again, if we start off with propene, notice that the 1 is not included. It's assumed to be on 1. And it reacts with hydrogen bromide. So this is asymmetric, and the position of the double bond is asymmetric. If I drew a line vertically here, you would see that what's on the left-hand side and the right-hand side is different. You get 2 products. You get one where the bromine's on the second carbon in and one where the bromine's on the first carbon. Now, this is known as the main product, and this is the minor product, major or minor. Now, the main product could be 99% and the minor could be 1%, or it could be 55% and 45%. That you are not required to know. So we need a rule to explain this, and the rule is here. When you're looking at a double bond, The carbon involved in the double bond that has more hydrogens, which is this particular carbon here, okay, it's got 2 hydrogens attached to it, where this carbon involved in the double bond only has 1. The one that has more hydrogens to begin with gets the additional hydrogen for the major product. So that's why this one is the major. And this one is the minor, where the reverse is true, where the hydrogen goes to the second carbon in. So again, when you're trying to apply Markovnikov's rule, and you only have to apply it under one set of conditions, where the double bond is placed asymmetrically in the molecule, and when the reactant adding over the double bond is also asymmetric. If those 2 conditions are met, you must apply Markovnikov's rule. You look at the double bond. Which of the carbons has more hydrogen? That's the one where the hydrogens go in the major product. You will be expected to apply Markovnikov's rule to predict products every single time you have something adding over a double bond. So please work through examples with Markovnikov's rule. The homework is listed here. I would suggest you work through the tutorials first, and then we will continue on in our study of organic chemistry. Briefly, these 2 infographics here show some compounds that have a lot of double bonds in them. Oftentimes, a conjugated double bond system, which is what you're kind of seeing here with the color of roses, meaning you have a double bond on every second carbon. Usually those compounds have a lot of color associated with them. So many dyes and pigments actually have that. Take a read of these 2.